Alright, 1.3 Vertex degree and counting. So we're starting to wrap up our first chapter of material. We're about halfway there. So in this section, we're going to start introducing some properties of the vertex. And also today, we're going to go ahead and introduce our first algorithm of the term. So to start us off, let's go ahead and start with a definition. Actually, two definitions I have here. First one is, let's talk about the open neighborhood of a vertex. So recall from our previous lectures, we talked about what it meant for two vertices to be neighbors. Well, whenever I talk about the open neighborhood of some vertex v, I'm going to denote this with an n sub g of v, or just n of v. If I'm working with more than one graph, then I probably want to put n sub g of v, like what I have here. But if I know I'm working with just one graph, it suffices for us to just put n of v. So these are the set of all vertices that are adjacent to that vertex v, or in other words, the set of all neighbors. If I want to be a little bit formal with my notation here, I can write that the neighborhood of v is all the vertices u such that there's an edge connecting u and v. So we have our first definition. If you look in the notes, we also have some other related definitions such as closed neighborhood and things along that line. The next definition I'm going to go ahead and introduce is the degree of my vertex. Here I use d sub g of v, or d of v. Again, if I'm working with multiple graphs, maybe I want to use a d sub g of v. But if I know I'm working with just a single graph, then I can just say d of v. This is the number of edges incident to v, or you can also say that this is the number of neighbors of a v. So that's why if we have this equation right here, d of v is the size or the number of neighbors. After talking about degree, one thing that we may be also interested in is the maximum and minimum degrees of a graph. So the maximum degree, here I'm going to use this notation, a capital delta of g. Well, this is exactly what it sounds like. This is the largest degree in my given graph. Whereas the minimum degree is also defined in the same way. Here we use a lowercase delta of g to denote the minimum degree, that is the smallest degree in my graph. So we have the neighborhood, the degree, the maximum degree with a capital delta of g, and the minimum degree denoted with a lowercase delta of g. So we have some nice definitions. And let's go ahead and look at this proposition that's related to these definitions. So proposition 1.3.1, and this actually has a name. We call this the degree sum formula. That is, if I have some graph, whatever it may be, then if I take the degrees of every single vertex and add them together, remember that's what this notation means right here, the sigma notation. This means I take all the degrees of each one and add them together. This is equal to 2 times, here we have the number of edges. So we have our degree sum formula. So if I have any valid graph, then it should follow this degree sum formula. That tells me that if I gave you a list of all the degrees of each vertex and a number of edges, then you can tell me very quickly, can that actually be a true graph? Is that something that we can actually draw? So this is our proposition. The proof for this is actually just one sentence long. You can actually see this in your notes. I highly recommend that you take a look over it. Moving on, the next thing I'm going to talk about is our next definition, the degree sequence of a graph. So if I look at a graph, or a vertex in a graph, I can determine its degree just by counting the number of edges. Well, one thing we might also be interested in is just listing out the degree of every single vertex that we have in my graph. This is what we call the degree sequence. And usually we write this in non-increasing order. And you'll see what I mean by this in just a moment when I pull out an example. So Along with a degree sequence, I also want to define this thing called a graphic sequence. So if I have any list of numbers, a sequence of non-negative integers, then I can actually say that that sequence is graphic if it is a degree sequence. So to clarify on this, a degree sequence is where I give you a graph and then you can list out each degree. For a graphic sequence, I may say, here's a random list of numbers. Can you tell me if it's graphic? To prove that it's graphic, I'm asking, can you show me that it is a degree sequence? So let's go ahead and look at a quick example to see what do we mean by a degree sequence. So here I have some random graph that I've just drawn up very quickly. Let's go ahead and count the degree of each vertex. Starting here with the top left, this only has one edge connected to it, or in other words, it only has one neighbor, so it has degree 1. Similarly over here, this should also be degree 1. It only has one neighbor. And then for these remaining 3, we can very easily and quickly verify that each of these are connected to 2 neighbors. That is, I have 1, 1, 2, 2, 2. So if I want to write the degree sequence of this, remember here I put in the note that I want to put it in non-increasing order. In other words, I want to start from the largest and then go down to the smallest degree. So if I want the degree sequence of this graph, I'm going to go ahead and put this down as, in my little curly brackets, 2, 2, 2, 1, 1. So this is the degree sequence of this given graph. Let's go ahead and do another example, just for practice. Here I have another graph that I've drawn. In particular, this graph is disconnected. It has 2 components that are not connected to each other. And then we can go ahead and count the degree of each vertex individually. For these vertices on this other component on the right, they have a degree of 1 each. Whereas the degree of the vertices on this triangle are of degree 2. So if I were to write this in a degree sequence from largest to smallest, I would have 2, 2, 2, 1, and 1. So you might be looking at this and noticing something. Both of these graphs have the same degree sequence. This is actually a really important note because this tells me that a degree sequence does not uniquely define a graph. That is, you can have a degree sequence and it can represent multiple different graphs, especially if we're talking about connected or not connected graphs. So this is an example of a degree sequence. So whenever I'm looking at this, if I give you a graph, it's not too difficult to find the degree sequence. You can just count the degree of each one and then write them down from largest to smallest. But what if I give you a sequence? Can you tell me, first off, is it a graphic sequence? That is it a degree sequence? And furthermore, can you draw me a graph that matches that degree sequence? So on that end, it's a little bit more difficult. So here we're going to introduce our first algorithm of the term. So this next slide is going to be a little bit heavy on text. So we have theorem 1.3.1. This is the Havel-Hakimi algorithm. This was actually discovered separately by 2 different mathematicians. First one by Havel, I believe, in 1955, and Hakimi in 1962. They both found this algorithm independently of each other, if I'm remembering correctly. So whenever we talk about algorithms, a lot of times we want to discuss algorithms in terms of an input and an output. That is, what do we give the algorithm and what do we want the algorithm to return back to us? So reading through this, for n greater than 1, an integer list d of size n is graphic if and only if d prime is graphic, where d prime is obtained from d by deleting its largest delta element delta, and subtracting 1 from its delta next largest elements. Furthermore, the only one element graphic sequence is D1 equal to 0. That's a very wordy for us. Let's go ahead and continue this formal view of it, and then we're going to do an example. Whenever we see this example, we're going to see that even though this is a very wordy algorithm, it's not too involved for us. So as I mentioned, we have an input that is a sequence, some list of numbers. And what we're going to do with this algorithm is that if I have that sequence, I can quote unquote reduce that sequence into a smaller sequence. And then I'm going to repeat that over and over again until I get something that I can easily verify is graphic or not. Here, initialization, this represents what do we start with. Iteration, this is our process of one computation work. And output is our final result. So if you need to, take a moment to pause the video right now and really read through this. I'm going to do an example as we talk about it. So, talking about our example, I want to show that this sequence 3, 3, 3, 3, 3, 2, 2, 1 is graphic. That is, I want to verify that it is a degree sequence. Then, if it is a degree sequence, can I make that graph that has this given degree sequence S? So in order to do this, I'm going to go ahead and apply our Havel-Hakimi algorithm. And I'm going to manually process this. If you're a little bit familiar with programming, you could also put this into a computer program and figure out if this is a graphic sequence as well. So let's start off with our first process, or in other words, more formally, our first iteration, iteration 1. So here I have my first sequence that I was given. The Havel-Hakimi algorithm says I delete the first entry, 3, and then I subtract 1 from the next 3 entries. So I remove the first entry, and I subtract 1 from the next 3 entries. If I do that by deleting this first entry and subtracting 1 from these first 3, I have 2, 2, 2, and then I didn't touch the rest of my sequence. So again, I want to emphasize, I deleted 1 entry, the first one, and I deleted 1 from the next 3 entries. I knew to delete 1 from the next 3 entries because I deleted 3. In other words, if this was like a 5, then I would delete that 5 and I would subtract 1 from the next 5 entries. Alright, so I did my first part of the iteration, and I need to reorder this because a degree sequence is from largest to smallest. And here, clearly I'm not from largest to smallest. So if I reorder this, I have 3, 2, 2, 2, 2, 2, 1. So notice here that I started off with 1 sequence, and then I reduced it down to a smaller sequence. Originally, I had 1, 2, 3, 4, 5, 6, 7, 8 entries, and now I only have 7 entries. So this is 1 iteration of my Havel-Hakimi algorithm. And so far, this is a little bit not obvious to see if this is graphic or not. We're not really sure yet. So let's apply our iteration once more, our algorithm once more. That is, let's do iteration number 2. So I have my new reduced sequence, and I'm pretty much going to follow the same pattern. I look at the largest term, in this case 3, and I'm going to delete the first entry and subtract 1 from the next 3 entries. Again, I know to subtract 1 from the next 3 entries because I deleted a 3. If I do that, I am left with 1, 1, 1, 2, 2, 1. And once again, I can reorder this from largest to smallest. So I have this here. So once again, I reduced this into a smaller, shorter sequence. Unfortunately, I'm still not sure if this is graphic. This may be a little bit difficult for us to see if it's graphic or not immediately. So let's do it again. Let's apply our algorithm once more. So let me clear the screen here. So iteration 3, I have that reduced sequence I had from my previous iteration. And then by the Havel-Hakimi algorithm, I look at my largest entry, 2, I delete it, and I subtract 1 from the next 2 entries. Again, I'm subtracting 1 from the next 2 entries because I deleted a 2. If I do that, I'm left with 1, 0, 1, 1, 1, which if I reorder it, I'm left with 1, 1, 1, 1, 0. So I'm going to claim that this should be a fair amount enough for us to check if we're a graphic or not. By our algorithm theorem, we know that my original sequence is graphic if and only if my output, in this case 1, 1, 1, 1, 0, is graphic. So just to recap on what our algorithm did, we started off with this algorithm. We reduced it down once through iteration 1, did it once more to iteration 2, and went to iteration 3. So all of these sequences are graphic if at least one of them is graphic. So let's go ahead and check our most simple sequence, 1, 1, 1, 1, 0. Is this graphic or not? So remember that each of these represent a vertex and its degree. So whenever I look at 1, 1, 1, 1, 0, I have 1, 2, 3, 4, 5 entries. That means I have 5 vertices to work with. And in particular, let's just go ahead and see what happens whenever I draw an edge between any arbitrary pair. So let's say I draw an edge here. Whenever I draw an edge here, now I have that these two vertices have degree 1 and 1. So these two are covered. But what about this vertex over here? These two over here? Well, I can draw another edge. And I can see, well, this vertex has degree 1. This vertex has degree 1. This one also has 1. This one has degree 1. And this last vertex has degree 0, which matches what we're looking for. In other words, we played around with it a little bit to see what's going on. So I have a graph that matches my smallest sequence. This tells me that 1, 1, 1, 1, 0 is in fact graphic. By our theorem, since this bottom sequence is graphic, then the rest of these must also be graphic. So yes, my original sequence is in fact a graphic sequence. If it was impossible to draw this picture, then I would say no, it's not graphic, hence my original sequence cannot be graphic. It's an if and only if relationship for us. So now, how do I start by getting back to this original sequence? How do I construct a graph that matches the original sequence? Well, I already have a graph that matches my reduced sequence at the bottom. What we're going to do is we're going to, in a sense, reverse engineer this. We're going to go step by step. We're going to construct a graph that matches this third sequence. Then from there, we're going to construct a graph that matches the second sequence. And then from there, we're going to construct that graph to match the very first sequence. So let's see, how do I get from the fourth to the third sequence? So what I like doing is I like pointing out what's common between these two sequences. Well, if I look at these two sequences very directly, both of them have 1, 1, 1 within them. And that's not a coincidence because, well, that means if I want to create my new graph from my currently existing graph, that means 3 of my vertices of degree 1 are going to stay the same. They're going to be untouched. So for these ones that I've boxed, I'm not going to do anything with them. I'm going to leave them alone. The next thing I note is that in my third sequence, I have an extra vertex of degree 2. So what I'm going to do is I'm going to add a new vertex to my graph. And then it needs to be degree 2. That means I need to draw at least 2 edges, not at least, exactly 2 edges connected to that vertex. Well, if I'm looking at my vertex that I've circled here, if I want to draw 2 edges, I can't touch these 3 in the boxes. That means my only options, or some good options, are if I do one edge to each of these remaining vertices. So again, I had needed 2 edges, and I had 2 vertices that could be touched. So here, I drew my edges. So I claim that this right here is actually a graph that matches 2, 2, 1, 1, 1, 1. And let's go ahead and double check. I want 2 vertices of degree 2. I have a vertex of degree 2 here and a vertex of degree 2 here. And then I need my remaining vertices to be of degree 1, which is also true. So I went from the 4th sequence to the 3rd sequence. Now let's move from the 3rd to the 2nd. And we're pretty much going to do the same thing. I'm going to point out what do they have in common. Well, these sequences have a pair of 2s and a single 1 in common. That means if I look at my graph so far, I can go ahead and look at 2 vertices of degree 2. In this case, I can look at these top 2 on the right, and then 1 vertex of degree 1. One thing that I really want to point out also, I chose this vertex of degree 1, but that was completely arbitrary. I could have chosen any one of these 4 to be my common vertex of degree 1. But anyway, here this means once again I'm not going to touch these vertices that I've boxed in. The only vertices I may touch are these remaining 3. Next, again, my 2nd sequence has 1 more vertex. So I'm going to add a new vertex, and since it's degree 3, it needs 3 edges. And I have 3 vertices that can be modified. Thus, I'm going to draw an edge to each one. And then I claim that this will match our 2nd sequence. Let's see if it matches 3, 5 2s, and a 1. Let's see, I have a vertex of degree 3. I need 5 vertices of degree 2. 1, 2, 3, 4, 5. And then 1 vertex of degree 1. So we're good here. Now we can finally do our last step, moving from the 2nd sequence to the 1st sequence. And I'm going to do this exact same pattern. I'm going to point out their common similarities, and then I'm going to point them out in this given graph here, arbitrarily. So I need a vertex of degree 3, 2 vertices of degree 2, and a vertex of degree 1. Again, for my vertices of degree 2, I just arbitrarily chose a pair. You didn't have to choose these 2 specifically. You could have chosen this one up here in the middle, and then this one over here on the right, or even this bottom one. I'm arbitrarily choosing some vertices of degree 2. Since my first sequence has an extra vertex, I'm going to go ahead and add that in, and it needs to be degree 3. Once again, I need 3 edges, and I have 3 vertices that are untouched so far. So I'm going to draw an edge connecting them to my last vertex. And thus, I get a graph that matches this degree sequence. And we can verify this very quickly. So this is my application of the Havel-Hakimi algorithm. Alright, so that's all for this section. And this will actually be our last video for Module 1. We do have a section 1.4, but since it's a very short section, it talks about directed grabs. Again, I do recommend that you take some time to look over it, 1.4. All right, have a good one.